Hello, welcome to another class of digital design with Verilog. Today class will discuss about RTL design and in particular algorithmic state machine design. So, any digital system whenever design, so FSM is good for smaller examples. So, whenever the example are bigger in real life systems, FSM have some issues. So, that we will discuss in today classes. Outline of today class is drawback of finite state machines. We have already discussed about finite state machines. We can design very good digital system with finite state machine, but there are some important or interesting drawbacks of FSMs are there. So, that is why we need to go for some better models to design digital system. So, better model is algorithmic state machines, which comprise of FSM plus data path, FSM plus DP. And in FSM, so algorithmic state machines, so what are the building blocks of FSM, and then how we can model. First, some set of examples we looked at how we can model the general FSM using ASM, then we will go for proper ASM designs. So, reference material for this lecture is chapter 8 of Manu book. So, whatever our reference book, digital design at RTL level, and chapter 15 of Kumar book. So, A. Anand Kumar, Fundamental of Digital Circuit, 3rd editions. So, these are the two books we take material from these two books. And first let us discuss what is the drawback of FSM, what is the drawback of finite state machines. So, FSM for smaller example is fine. So, whenever there are a lot of data involved in digital system, particularly sequential system, it is very difficult to model using FSM. So, how it is difficult, let us see. So, whenever many input and many outputs are there, it is awkward to list all of these H transition arc in FSM. This is one reason. On any given arc, so in general what happens in real life systems? So, typically most inputs are do not care, typically most output are unchanged from the setting in the previous states, and it is really tedious and repetitive to do list all the state and all the input outputs exhaustively. So, it is not necessary. Okay, so, in FSM these are the major drawbacks. So, it is not a clear structure for illustrating or designing control flow. And what about generic memory or data? Suppose you take 64-bit memory, okay, 64-bit memory or 64-bit register. So, in a 64-bit register, so we can model 64-bit register using FSM, but whenever you want to design FSM for 64-bit register, so how many states will be there? 2 to the power 64. We will not be able to tabulate, we will not be able to draw the FSM for 64-bit register. That means, we will not be able to model a register using FSM. 32-bit register, 32-bit counter will not be able to model. Then what is the use of FSM then? So, this is the major drawback. FSM have problem of state space explosion. So, whenever the data components or memory components use larger bits, then it is very difficult to model using FSM. So, what about this generic memory or data? And we say, do they really need to be part of the states? If you have many bits of data, this would lead to a huge states, huge number of states. Example, state diagram of counter or shift register is really pointless. 32-bit counter have 2 to the 32 states, and in a digital system, suppose you are using a counter, 32-bit counter, and we want to represent using FSM, then it is actually useless, it is of no use. and it is similar analogous to conventional circuit design. So, conventional circuit designs using truth table is okay or easy for small problem. It is okay or easy for small problems, but whenever the number of input and output grows, then truth table method is completely useless. It is not, it cannot handle. Okay. Suppose you want to design a adder, 32-bit adder, or suppose 16 input MOX multiplexers. Can you design using truth table method? No. Truth table method get out of hand, because you will not be able to table the input output using truth table for a 32-bit adder. This absolutely we cannot do, because 2 to the 32 listing out 2 to the 32 input. Suppose you are using 32-bit adder, then number of input will be 32 for one input, another 32 for another input, and output will be again 32. So, 2 to the 64 input, different varieties, and is very difficult to handle. And not only that, so we require to handle 32 output functions also. 32 output functions of each functions having 2 to the 64 different values. So, which is we cannot do. Similar to that, so in FSM also it is similar thing. So, design 2 level circuit for 32-bit adder is using truth table methods is really useless or is not desirable. 64 input, 32 output, 32 or 33 output using truth table method. Worst case delay will be 2 to the power 63 OR gate delay, because how many worst case, how many number of 1 will be there in the truth table, because truth table have 2 to the 64 thing. So, 2 to the 63 OR gate delays will be there, and worst gate size will be number of product terms. So, this was just number of product term, which is 2 to the power n minus 1 minus 1. So, number of product term if grows like anything, 32 means 2 to the 32. So, it is not desirable to do truth table method of designing a adder or multiplexers. As this problem is in combinational circuit domain. Similarly, in sequential circuit domain also we face this exactly similar issue. Whenever we want to model a register, a counter of more than 16 bit or 32 bit, then the FSM size get out of hand. We will not be able to design using hand. Also, it is not desirable to do with computer also. So, in case of adder, so we use prefix sum methods, carry locate method, use different approach to get the circuit, optimize circuits, not the RCA ripple carry adder, we use go for prefix sum standard algorithmic method to do this thing, but we will not do with actually truth table methods. Drawback of FSM as discussed earlier. So, some problem of sequential design, small problem, it is design is very easy. So, in earlier classes we have designed FSM for many digital problems, digital design sequential problems, but in real life digital design problem where data is more useful, data oriented, state diagrams are not helpful, FSM are not helpful, whether it is Moore FSM or Mealy FSM, both are not helpful. Already stated, so state diagram of 32-bit counter or shift register is pointless. Suppose 32-bit counter have 2 to the 32 states, and the solution is ASM, algorithmic state machines, or FSMD, finite state machine with data, or we can say RTL based design, register transfer level design. So, we include register for storing data, and then design. So, that means memory element we try to what I can say make out of the design, particularly data path, memory element and actual compute unit we make out of the state machines. So, all terms ASM, FSMD and RTL based design all are similar thing, all three things are similar thing. So, ASM, FSMD, RTL are similar terms. ASM means algorithmic state machines, FSMD means FSM with data path, RTL designs we use a register transfer level design. Okay. And in this case, particularly whenever we say ASMD or ASM, FSMD and RTL design, so what we basically define is define what work to be done at each clock cycle. So, what we do is define what work to be done at each cycle, that get decided, and we try to emphasize on cycle based design and what work to be done. This work can be little bit loading to register, incrementing counter, additions, multiplications, little bit bigger work. Algorithmic state machines, another representation of finite state machines, another representation, improved versions we can say, with data elements, compute element and selection elements are separated, particularly adder, multiplier, counter, registers and multiplexer are separated from the actual FSM. Okay, FSM with data path, we can say FSM with data path and suitable for FSM with larger number of input and output. As compared to FSM, it is expressed using state diagram and state table in FSM, but in ASM, so it is also similar, but we include one more thing. So, that is actually FSM part and data path, we separate it out, and FSM we generally describe using ASM in this case and data path are separated. So, in this way ASM is more powerful as compared to FSM. So, in this case ASM, in general we generally separate controller and data processor, data path and controller we separate it out. ASM we need to separate controller and data path or data processor. So, controller, what action to be taken, what is the fundamental operations or operating mode that get decided, what get done at what cycle, controller decides. Controller take input from external world, also status. Processor undertake actions, manipulate the data, store the data, okay, increment or decrement counters. So, it undertake the actions, processor or data path do the undertake the actions. Controller decide what action to be taken. So, ASM have actually both controller and data processor. Controller is almost similar to FSM, we can say, but whenever you include both, it comprises of ASM. The ultimate goal is to design in RTL. Ultimate goal is RTL designs and design using control path plus data path. So, we are separating both control path and data path, and in our design both will be there. So, design using control path plus data path. Control path means controller part and data path approach means it is processor part or processing part, that we call as data path, control path and data path we call as data processor also, which undertake actions. Who provide actions? Controller provide actions. Processor do the actions. And very high level view we can see is this part is actually control part, clearly this part is control part. So, control part have actually same as FSM. So, it take status as input and it provide commands or what action to be taken, it get decided by FSM or controller. This is the controller and this is the data processing part. In the data processing part, so we get data means from external we get input, also we can send data to output to the external, that means IO get interface with the data processing part. And what are the component of data processing part, particularly register, shift register, adder, counter, multiplexer, ALU, then multiplier, in this case multipliers, divider, any kind of computational units will be there in data processing part. And ASM use these concepts. Okay. So, whenever you implement ASMs, we will have both data path and control path separated. Our circuit is now explicitly separated, data path is separated and control path is separated. So, we say in this case left side is the control path, it is purely, whereas you can say it is FSM, and data path is this is data path, and clearly ASM, whenever you say ASM is equal to FSM plus data path, this part is data path and this part is FSM. ASM is we can model ASM, and whenever you implement it is actually separated out control path and data path. Okay. So, because of this separations, ASM is more powerful. Also another most interesting thing is in ASM we can model both Moore machines, Moore FSM and Mealy FSM. So, that is also another most interesting. So, let us go back to this earlier classes and just remember this serial additions. So, in the serial additions, this is the diagram. So, in this case what we are doing is actually there are two register A and B, and every cycle we are taking two rightmost bit here and we are giving input to this full adder and we are calculating sum and carry, and this full adder for every bit values it calculate the sum and carry, and this carry get feedback to the full adder again. So, this is what we are doing. So, suppose n bit A are there, n bit B are there, we are adding two n bit numbers and storing it A. A is equal to what operations we are doing? A is equal to A plus B. So, here what we require? Every cycle we require a shift control, whether we are doing shifting or not, and in this case this shift control, this clock is coming and clock is because register are clocked, both register A and B are clocked and this flip flop is clocked. So, clock is connected to registers and this flip flop, and in this case clearly shift control is ended, this clock is ended. So, that means this shift control will enable this flip flop, otherwise it will not do. So, in this case this is the already you have studied in earlier classes, this circuit will do, suppose A is 8 bit, B is 8 bit, then it will take two 8 bit numbers A and B and it will add both the numbers and store back in the A, and it is serially it will do. So, if you do something like A0, A1, A2, A3, A4, A5, A6, A7 and add with B0, B1, B2, B3, B4, B5, B6 and B7. then it will do first A0 B0, next A1 B1, next A2 B2. It will do serially from the right one after another, and this one is we are doing shifting right. Every clock cycle we are shifting one bit and giving input to xy, and it generates sum and carry, and this carry get feedback, that means carry get used in the next bit. Whatever carry generated, it get used in the next bit in the next clock cycle, because this flip flop get enabled or used for the next clock cycle. In this way you can do serial addition of two numbers using one full adder, and this circuit do A is equal to A plus B, and whatever the things resultant thing, it gets stored back into A. So, this is actually only data path. This shows data path of serial additions, not the control path. How this shift control and this thing will be get controlled is we are not aware of that, and how to do we do not know. So, we will design in this course. So, in the today class or maybe next classes we will do that thing. So, if you want to design the same thing, so the serial additions, then what should be the control part or control path? So, ultimately, so we are doing for suppose 8 bit. So, somehow we need to start CTRL equal to suppose 0, and it need to go up to 7, CTRL equal to 7. This I, for I is equal to 1 to 7 similarly. So, we need to do for 8 times, that we need to, and whenever this circuit get a go signal, then only you should do. Okay. So, if you look at the things, so this is the high level overview of control path of this thing. So, initially if go is equal to 0, then it will be in start state. If go is equal to 1, then it will load the value, So, particularly load the value into A and B and clear what it get clear, clear the flip flop, what are the D flip flop, clear the flip flop, and after that every cycle it will increment the things, and it will run for up to, in our case previous case, suppose n is equal to 8, then it start with 0 and goes up to 7, and when control is equal to 7, then it set done. That means, it will do for 8 times, So, it start with 0, 1, 2, 3, 4, 5, 6 and 7, and it's whenever it reaches 7, it stop. So, till it is not 7, it's 2 in a loop. So, this is for I is equal to 0 to 7 we are doing, 0 to 7. So, for 8 times we are doing for 8 bit data, and this is actually what, but at high level we can say this is control part. At high level this is control part. And this is a serial addition data path. In this case what we are doing, C is equal to A plus B we are doing. So, there are one register A, another register B, 8 bit register, suppose it may be general, okay, n bit register, and every time. So, we are doing one, this is the full adder, and this is the flip flop which store the carry bit. So, initially we are clearing the carry bit, clear signals, and these things, there is a comparator, there is a comparator, there is a register where you can load and increment. So, there are two operations in this register is required. One thing is load, this register can do load 0 or increment. increment. And here there is a comparator which can compare the current control value with n. And if it is, this is what are the control values. So, this is a control value, it comparator, it compares if it is what you can say, this is equal to n, less than n and greater than n. So, these three things. So, if the control is equal to n, then this is output, it will give output that my things is done. This is data path, this one is data path, okay. And go we are giving from outside, done means CTRL is equal to n, it signifies it is done, okay. And this is outside world. So, there are two input A and B, it store into register and do the computations, and then once computation is done, we get output into the outside world. This is the data path, this one is serial addition data path, okay. C is equal to A plus B it does, and it does serially, and it takes n cycles, okay. Suppose n bit, it takes n cycle, and its control path was this one. So, this one is control path for the serial additions. So, at high level we are showing this, but whenever you go and design ASM, we require proper way of designing the things. This is at high level, we have shown controller look like this, controller look like this, this controller look like this, and this may not be included, this path, this is part of the data path. So, this is the red part is the controller part, and this one is the data path. So, here in the data path we have a full adder. So, we have 3 registers A, B and C, we have a comparator and we have a register, we have a D flip flop, and what input it can give. So, in the data path inputs are clearly this n is input, okay. This n is input, this A and B is input, this is C is output, and go is again input. So, whenever go means it gives the go command, then it do the work, okay. Whenever go commands comes, then control is equal to 0, and for every cycle it is actually, here we are not showing the cycle. So, here these all sequential elements, particularly register, this register, this counter and flip flop, all are clocked. That means clocked are default input. In this case we are not showing, but it is default input. So, in this case go is command, it get from the data path, done is again it is give to the outside world, okay. So, overall it looks like data path look like this for the serial additions. It may be different, what we are thinking is it may look like this, okay. We are trying to design serial additions, control path and data path at high level without learning about ASM. So, now let us see, so how we can model using ASM. So, what are the component of ASM and how it separate the control path and data path. So, in ASM designs, so particularly data processing, so what sort of manipulations of the input and output are requested, that thing we can put. How many or what sort of things need to be stored, that get also decided, okay. First thing is what sort of manipulations of the input and outputs are requested, how many and what sort of things need to be stored, and ultimately how to designs. So, we can go for ad hoc or creative or by insights way somewhere we can designs. List requested operations and manipulations for the problem statements, include initializations and conclude, this is must. So, particularly in earlier case whenever go is equal to 1, then only it start the doing operations, and include status line whenever the work is done, control is equal to n. So, that gives status done. So, how to design? These are the include initialization control, include status line, and list requested operations and manipulations. So, these are the very crude way of thinking and doing the things. Okay. So, we will have many examples. So, given the English like statements, how we will come up with ASM and how we will infer the data path and how we will design the data path, that we will have many examples. So, ASM control path. So, all of the commands to the data processor logic need to be controlled, all the status line need to be monitored and acted upon. So, if we look at the thing, so ASM design have two part, controller path and data path. So, FSM send all the commands, okay. All the commands to the data processor, data path logic need to be controlled. This is the control path work. Also, so after doing some operations from the data path, okay, suppose data path do some operations, then after doing the operations, all the status line what happened after doing operations need to be monitored, and based on that we need to act. FSM need to act. FSM need to act. ASM charts are like state diagrams, but without specific drawback. Okay. So, in FSM case, what we list all the input for each transactions. Okay. So, FSM correctness and FSM completeness we looked at, but in ASM case the things are little bit different. So, we do not list all the input for each transactions, because for real life bigger problems, so we will have actually many do not care inputs, we do not need to list. Okay. So, do not list all output for each state. So, why to list all output for each state? So, if output is not required in that state, why to list? When output do not change in many of the states, why to list? Okay, we can ignore. Okay, so kind of things if you include many do not care in FSM, then what will be the resultant one will be the ASM. But in specification why to do, in the tabling why to do. So, let us skip it kind of thing. Okay. So, ASM philosophy is FSM with this kind of improvement kind of thing, so that we can go for a bigger design. So, how to design? So, ASM chart or state diagram for small problem. So, state assignment, state table is good, just like for combinational part already we have discussed. So, K map for gates, flip flop, register, mocks, decrements, decrementer, EPROM, or creatively a combination of them. Okay. So, for small problem how to design. So, this is actually for small problem anything is fine. So, there is no what I can say difference, you can do it similar way as ASM. So, ASM charts are like flow charts with a very crucial difference. If you compare ASM chart with or ASM design, ASM chart with flow chart, regular flow charts. Flow charts do not have actual timing informations or cycle informations. So, and they do not have states. Okay. So, ASM charts are like flow charts, but with specific crucial difference that is called timing informations. So, particularly ASM we are bit careful, especially with timing. So, three type of component or boxes or three type of component we use in ASM design. So, one is state box, other one is decision box, and third and most important box is actually that is called combinational box, transition box, or we say it is conditional box. So, we will term as conditional box. Conditional box. So, ASM design use three things: state box, decision box and conditional boxes. These three boxes in general we use, and by default arrow we use. So, in FSM also we use transitions arrow. So, what are the three elements? So, three elements are with state box is exactly same as FSM state box. So, where we every state box have state name, then output signals or actions, where we can specify more type of FSM. That means, at each state what will be the output, what will be the actions. So, we have conditional expressions. Okay. So, this is called decision box. So, in flowchart we use decision box. In finite state machines FSM we do not have decision box, but in ASM we have decision box. Okay. In flowchart we have decision box. So, FSM do not have decision box. Okay. Flowchart do not have this kind of state. Okay. This is purely mixture of flowchart and FSM. We are trying to track cycle, also we are trying to make it like flow. Okay. So, ASM have decision box, any conditional expressions for yes or no. For yes it will go to one path and for no it will go to another path, decision box. And there is a most interesting another kind of box we use in ASM modeling is conditional box or conditional output box. So, this is conditional output or actions based on some conditions. Just after the conditional decision box we can put conditional box. Okay. So, we will have many examples. So, on the arc of any decision box we can put conditional output box. Okay. So, in this arc we can put a conditional output box. That means, if this condition occur then this will be the output. Okay. So, conditional actions also we can take and we can put conditional output. So, this will help us to model Mealy kind of FSM, Mealy type of FSM. So, clearly in ASM probably we will be able to model more machines, Mealy type of machines. Also we have a regular flow kind of things, we have a decision box. Decision box. So, in because of this combination of these three things, it makes more powerful as compared to regular FSM, also as compared to regular flowcharts. ASM have timing informations, ASM have we can model both mode type and Mealy type of ASM. Because of these three things, combination of these three things, ASM is more powerful, and on top of that it separates both control path and data path. Okay. So, this four things makes ASM more powerful in modeling any digital system, bigger digital system. And state box. So, what is state box? State box is one box per system states, and we can specify operations, and state box have name. Also optionally we can put encoding, just like FSM encoding, So, here also we can put what code we will assign for the state box, that also we can put optionally code for encoding. So, state box have operations or actions if you reach in the states, or output, actions, output, operations and output we can specify, and this state of name, what encoder you are using, code for the states we can use encoding, state encoding of general FSM. So, state box, one box per system states, that means whenever state box we say, suppose a ASM have 3 state box, then it have 3 states. So, state box decides how many states are there in ASM, and this code is optional binary state code, which is binary encoding or its encoding values. And this operation notations, in general whatever we do operations, so or actions we state in state box, just like for example, sum equal to 0. So, sum get loaded to 0, carry is initialized to 0 or load A. Okay. And we can use combinational value s is equal to 0 or t is equal to s plus b, this kind of statement, this is addition statements. What kind of operations, RTL kind of operations was register transfer level operations were specifying. So, t is equal to s plus b, whenever I am saying t is equal to s plus b, that means we are reading from register S, we are reading from register B, adding them and storing to register T, T is equal to S plus B. So, this is actually, this kind of specification is called register transfer level specification, RTL specifications. Load A, this is again loading A from external values, this is also RTL kind of specifications. So, because of these reasons, we say we are specifying at RTL level. So, idea, keep the operations abstract and high level. So, and do not work in detailed language of processing logic. So, just like write sum is equal to 0 or sum is initialized to 0, not like very detailed one. So, clear sum register is equal to 1, not like detailed things are not required. We can derive later on what kind of data path we will use for this kind of operations. Operation will take place at the end of the clock period. So, this is one of the most important thing, operation will take place at the end of the clock period. Okay, so not the beginning. So, whenever it reaches to the state box, so we will define a ASM block. So, in a cycle whole ASM block get executed at the end of the cycle, that we will define later. And state box, so represent a state equivalent to node of a state diagrams or a row in state tables, and it contain a register transfer actions or output signal. Okay, so, and clearly we can model more type of output that are listed inside the boxes. This is output signal or actions. This is more type of model you can do with state box. So, it is customary to write only the name of the signals that has to be asserted in the given state. So, write z instead of z is equal to 1. Z is initialized to 1. So, the same as z. So, z is equal to 1. So, that will give more compact form and easy to visualize. It might be useful to write an actions to be taken. So, count is equal to count plus 1 kind of thing. This is increment the counter, okay, or doing any RTL operations. So, write the action to be taken and only later translate it to asserting a control signals that causes a given actions to be taken places. So, whenever we are modeling the ASM, given the problem is modeling using ASM, then we write at a very high level. Okay. So, very abstract, count is equal to count plus 1 kind of. Later on we can, whenever it sends signal to the data path, at the later it translates to a control signal that caused the given action to take place. That means, count is equal to count plus 1. That means, this count value need to be incremented. If it is a counter, then it sends signal increment the counter values. Okay. Example, enable signal for a counter. This is decision box. So, another thing is decision box, the second type of box. Decision box basically conditions, logic flow control, similar to what we do in flow chart. So, and this decision box, only decision box depend on inputs. That means, maybe internally generated input or maybe from external input. So, whenever I say input in this case, it may be internally generated input or externally generated input. Okay. So, it depends on two inputs, this is input. So, if based on conditions, input conditions, so either it go for yes or no. Then, in case of general conditions is satisfied, if it is a boolean. So, suppose you are testing for some value b 0, suppose b 0 bit is 0 or 1 or some conditions. So, condition can be one expressions, okay, and boolean value test a particular bit or particular things. So, both are similar in this case. Decision boxes indicate that a given condition to be tested, the exit path to be chosen accordingly, similar to the flow charts. And the condition expressions may include one or more input to the FSM, and this decision boxes can be vector decision boxes. Okay. So, instead of 1 bit you can go for 2 bit or 3 bit vector of input conditions. Okay. Vector input conditions. So, here two things Z and Q 0. So, because 2 bits there you need to be 4 conditions, in this case 0 0, 0 1, 1 0 and somehow 1 1 need to be also there, and for every condition we need to specify the things. Okay. So, what will happen for all conditions? So, in general vector decision box are hexagon. Okay. So, and we need to specify all combination of this input decision variables. One input path entry point, a vector of input conditions placed in center of the box, that is tested, in this case Z and Q 0, and up to 2 to the power an output path. The path taken has a binary vector value that match with the input conditions. Here we are saying up to 2 to the power n. Okay. So, in this case this is 1 1 is not mentioned. Keep conditions as general as possible. So, preferably carry is high over this QFF5, output of flip flop 5, flip flop number 5 is equal to 1. So, this is actually very complicated. So, instead of writing like that, let us design at very high level, so that everyone can understand, and from there we derive. So, this kind of things are more complicated, because here data path and control path are separated. Let us make the things at high level. And in ASM the most important component is called conditional box, which is not available in flowchart, not available in FSM, regular FSM. But here to model melee machines FSM, we require this kind of things, and in ASM it is available. Okay. So, in melee machines what happens, every transitions have some output associated with that, every transitions. So, whenever every transitions have output associated with that, we want to model this thing using ASM, then we need to use the conditional box, and conditional box helps to model melee type of FSM. Conditional box, an action or operations to be undertaken conditioned on some earlier decision boxes. So, what it says, conditional boxes need to be get associated with decision box, that is must. Conditional output box without a decision box we cannot do. We cannot put a conditional box without a decision box, that is must. For conditional box, a decision box is must. We should have a decision box, otherwise we will not be able to do. Conditional box do not appear in normal flow charts. This is the major difference as compared to flow charts. The essential difference is timing. Flow chart are sequential, ASM chart are not sequential. All the operations associated with the given state take place simultaneously. So, all the operations associated with a given state take place simultaneously. Also, I am mentioning all the operations associated in a ASM block take place simultaneously. That we will see later. What is ASM block we will see later, but till now. So, let us see all the operations associated with a given state take place simultaneously. This is one statement. Second statement is for whole ASM block it takes simultaneously. Okay. That we will see. What is ASM block we will define later. This is conditional output box. So, denote outputs that are melee type, and the condition that are determined whether such output are generated is specified in the decision box. Okay. So, such outputs are generated is specified in the decision box, and it is useful to model melee type machines. ASM represents simple FSM. How we can represent very simple FSM? Algorithmic state machines can be used to model melee FSM, more FSM. They can also model mixed type. We can model melee FSM, we can model more FSM, also we can model mixed type of FSM. So, which is not melee type, which is not more type. We can model some mixed type of FSM. Some part will be melee type, some part will be more type. That means, ASM is more powerful as compared to both melee FSM and more FSM. So, algorithmic state machine is much better. Let us look at some examples. So, whatever we took examples. So, in the RTL design also we have set up around 12 or 13 examples. Okay. So, we will go through all examples one by one. So, in FSM also we took many examples. Let us redraw or redesign the same set of examples. Suppose D flip flop. This is FSM of D flip flop. Okay. So, D flip flop have two states. So, A and B. So, A is for outputting 0 and B is for to output 1. Okay. And this is the input D. This is the input D and this is the input. If input D is equal to 1, then it is written in 1. That means, whenever you are getting a input D is equal to 1, then by default it goes to state B, and whenever you are getting a input 0, it goes to state A, output is 0. Okay. This is the standard FSM for D flip flop, and we can model ASM. Means we want to convert this FSM of D flip flop to ASM of D flip flop. Okay. Algorithmic state machine of D flip flop. So, here it looks very similar. So, this one is what? State box. There are two state box A and B. Z is equal to output Okay. In state box B, output is equal to 1, state box A, output is equal to 0. This is the initial. So, maybe initially suppose this FSM is equal to suppose initial 1. So, this is initial line, okay. This one is initial line, okay. Then, so whenever D values, so suppose you are in state A, got a D, if D is equal to 0, this is the decision box. If D is equal to 0, then we are going to state A. If D is equal to 1, we are going to state B. Similarly, when you are in state B, based on the D values, if it is 0, then it goes to the state A, and if it is 1, it goes to the state B. So, it is very much similar to FSM design, very much similar. So, what we are trying to do is actually we are trying to draw or design some algorithmic state machine of D flip flop. First we have done FSM, then we have done the ASM. Without doing FSM also we can go directly to the ASM. So, this is how it looks like. Draw ASM of JK flip flop. So, this is the FSM of JK flip flop, okay. And this have also two states. There are two input J and K. Based on the value of J and K, it changes the state. This is the FSM of JK flip flop, okay. Correspondingly, so the ASM will look like similarly. So, this have also two states A and B. Here state A, output is equal to 0. So, whatever it specify here. State B, this is the output is equal to 1, same thing. And if you are in state A and based on the value of J, so what we are testing? Value of J, if J is equal to 0, okay, independent of K, okay, J is equal to 0, okay. If J is equal to 0, you are in state A, if value is equal to 0, okay. So, value is equal to 0, so JK value is equal to 0, then you are going to state A independent of K. So, here K value default output for both the cases K is equal to 0 and 1, for both the cases it is going. So, similarly for this case, if you are in state B, K is equal to 1. If K is equal to 0, suppose K is equal to 0, in this case for both the value of 0 1 case, it is going to state B, and if K is equal to 1 and based on value of K is equal to 1, suppose K is equal to 1, if you are in state B, K is equal to 1, suppose K is equal to 1. So, K is equal to 1 based on it independent of value of J, independent of value of 1 and 0. So, it goes to the state A. So, this is exactly similar model as compared to FSM. That means, we are able to model more FSM of D flip flop, JK flip flop using ASM. We are able to model both means JK flip flop and D flip flop using ASM. This is the ASM. And suppose you take, let us take another example of more FSM. So, this is this FSM is for detecting a sequence of two continuous one. Suppose W is input and W is continuously coming from W is equal to suppose 1 0 1 1 1 0 1 1 1, this is W. So, W is a stream of input coming, this is the first one, this is the second one. So, initially, so there is no means two ones because we are modeling using FSM. So, this FSM is A is equal to, initially the FSM will be in state A and in that case Z is equal to 0. So, whenever you got a first one, okay, so W is equal to 1, then it goes to the state B, and if you are getting a 0, that means you got only one 1. So, in this case it come back to state A. If you are getting a one more 1, you are in state B and you are getting a one more 1, then you are going to state C, and in that case we assert that the value of output is 1, z is equal to 1. Okay. And if we continue to do this thing, so suppose you are continue to get W is equal to 1, then it stay in state C and it output Z. Once whenever you get a W is equal to 0, that means input is changed, then it's come back to state A. So, this is the Moore type of FSM of detecting sequence of 2 1. So, a stream of stream of binary inputs are coming W, and for every clock cycles. Okay. So, this W have some values, sometimes it may change, sometimes it may not change, then what will be the output. So, this FSM shows that thing. So, this Moore FSM sequence, this is the present state, this is next state, and this is the output. So, how we can tabulate the Moore FSM for sequence of 2 1s. Okay, this is already we have discussed in the earlier classes, we are not doing detail. So, if you want to draw a ASM chart for this, algorithmic state machine chart for this, then corresponding ASM chart will look like this. So, this have also 3 state A, B and C, okay, and based on the W values. So, you are in state A, you are getting a W, okay, W is equal to 1, that means you are going to state B. If you are getting a again 1, then you are going to state C. Okay, similar, you are in state B getting a 1, you go to the state C. Okay. If you are getting a 0, A state getting a 0, you are in the same state. You are in state B getting a 0, you will go to the again state A. But if you are in state B and getting a 1, then you will go to state C, similar to this. And in state C, if you are getting a 1, you will continue to be in state C. If you are getting a 0, then you go to the state A. That means, any state, any states, whether this state or this state, if you are getting a 0, that means you will go to the state A. So, in this case also same, from A you are getting a 0 going here, from state B getting a 0 you are going here, from C also getting a 0 you are going here. And if you are getting a 1, then it changes. If you are in state A getting a 1, go to B. If you are in state B getting a 1, go to state C. If you are in state C and getting a 1, you stay in same states. So, here also we can model the sequence of 2 input, detecting sequence of 2 input 1 problem can be modeled using ASM. The same things. So, we can sequence of input 2 1s. Okay. So, that can be modeled using Mealy FSM. This is the Mealy FSM. So, in this case we can model the same thing using 2 states. We do not require 3 states. Okay. So, initially you are in state A, and if you are getting a W 0 input, then do not output anything, because here in arc we can specify output, that is the most important thing. Okay. If you are in state A, you are getting a 1, then output is equal to 0, but you are going to state B. If you are in state B getting a input 1, output a 1. Okay. And if you are in state B getting a 0, output 0. So, here with Mealy FSM we can model the same problem with 2 states. Okay. And let us do the same thing with ASM, because in ASM we can model Moore machines, also can model Mealy machines. So, this is the magic. So, we can model Moore machines, also can model Mealy machines using ASM. So, here there are 2 states A and B, okay. And here whatever extra thing is, you are in state B, you are in state B, you are in state B and getting a 1 will output 1. So, what was the same behavior of this Mealy machines were able to capture using ASM chart, and why we are able to do? Because of this decision box. The most important thing is the decision box. Okay, so, this is not decision, this one is conditional box attached with the decision box. So, this one is decision box, this one is conditional box. This conditional box attached with decision box. Because of this conditional box, so we will be able to or we are able to model this Mealy FSM, and because of this thing it is powerful. So, in this case clearly the arc of Mealy machines is actually modeled as combination of decision box and conditional box. So, arc of Mealy machines can be modeled nicely with decision box and conditional box, and decision box is used for regular flow charts. Okay. With these combinations it make it very powerful. This is ASM chart for 5 mod 5 counter. So, this is ASM. So, this is ASM, this is FSM 1, left side one is the FSM 1 and corresponding ASM chart. So, in this case this is also 5 states and this is also 5 states, and we are putting decisions based on the input, either it goes to the next state or it stay in the same states. So, this one is very simple one, okay. And what we are is output is equal to 1 when z is equal to 1. So, that means when you are in state 4 then output 1. So, in this case also what we are doing, if you are in state 4 then you got a output. So, same corresponding one, this things more, this is this one is not more Mealy FSM because of this thing, because arc, every arc is associated with output. So, here we can model the same thing. This is ASM chart of mod 5 counter, the left side one is Mealy FSM of mod 5 counter, right side one is ASM chart of mod 5 counter. The most importantly, example 6 ASM chart of 10 bit counter. The here what we are saying is FSM is not possible to draw tabulate, because 10 bit counter 1024 states, it is very difficult to draw. Even in computer also we can draw, but we will not be able to visualize in our computer screen. So, FSM is not possible, FSM not possible, okay, to draw or tabulate. So, this is the major drawback. This is called, this problem is called state space explosion. So, state space explosions. So, we will not be able to model a 10 bit or 20 bit or 32 bit counter, but the same thing we can model using ASM. So, you can model it 2 states, not 3 states, 2 states. So, S0 and S1. In S1 initialize the counter, and whenever you are getting a values you increment the counter. If counter reaches 1023 and if the x is equal to 1, then reset to c is equal to 0. This is a flow chart, decision boxes. So, we can model counter using flow charts. Okay. So, ASM chart we can model very nicely this 10 bit counter using ASM chart. And what the data path here we are specifying, c is equal to 0, this is a counter, c is equal to c plus 1, this is a counter. Now, this counter we are using as a data path. Okay. So, whenever you separate it out, so this counter loading and counter increment and comparison CMP these are counter loading, counter increment and comparison with 1023. These values are data path operations, these are DP operations. Because of this thing, data path operations were specified in the state box. Control flow will be specified in the flow. That means, control will be specified within the state transitions. Data path operations will be specified with the state box. Because both data path and control path are separated, we are able to model 10-bit counter easily using ASM. Okay. And because of that reasons, so we can put RTL like statements. So, these are the RTL like statements. Okay. C is equal to C plus 1. Okay. So, C is equal to 0, compare C to 1023. This is because of RTL like statements. And what is the summary of ASM? FSM have state space explosion problem. We can model both Mealy FSM and Moore FSM using ASM. Difference between flowchart and ASM is flowchart do not have timing informations. Okay. So, particularly timing, flowchart do not have timing information, ASM have timing informations, and with ASM we can separate data path and control path. With ASM we separate data path and control path. With high level statements, data path operations in state box and conditional box, it's make it more powerful to model many digital system. This is the summary of ASM, and in the next class we looked at many further examples, but in that case we looked at from the not only model, we want to implement the ASM also, okay, and how it can interface with the external world, that also we looked at. Okay. So, not only modeling the problem with ASM, how to implement and how it can interface with the external world and how data path and control path will be interconnected, that we will also looked at. Okay. See you in the next class. Thank you.